Hello everybody and welcome to the project presentation concerning the robotic arm. What we have done in this project is measure the movement of a human arm and let the robot reproduce this movement. Letting a robotic arm copy human movements has very interesting applications. At the moment, a lot of know-how is required to program a robot for every specific function that you want it to be able to perform. However, it would make the use of a robot much easier if they could just learn the task by performing the task once in front of it. Concerning our project, we'll start with a quick overview. In this figure, you can see the workflow that is used. We will start by measuring a performed movement with an Xbox 360 Kinect camera. This way we are able to retrieve three-dimensional data. This is still raw data, and to be able to use this data, regression will be performed. The trajectory is now available in X, Y, and Z coordinates. However, to program the robot, it would be much nicer to have values of the so-called joint space. This means giving angles of each joint of the robotic arm. Since the data that we've got consists of discrete values, there is still a degree of freedom for the inputs to reach these desired states. Using an optimization scheme, the most optimal input combination will be defined. The final step is feeding this desired and optimal trajectory to the robot. However, since modeling errors have to be taken into account, a control loop will be added using computed torque control. In the end, the robot should mimic the measured trajectory as good as possible.
Now we will show you how we measure a trajectory. With an Xbox Kinect, we track the position of the shoulder, elbow, wrist and hand of the moving arm. With the help of Python and MATLAB, we then can create this plot. The shoulder is the origin of the plot, and the green dots are the elbow, blue the wrist, and red the hand. We can already see that there's a lot of noise on this data. Definitely over here, we can see data points which don't contribute to this movement. For this reason, we will have to clean up this data, and this will be done with the regression. The regression on the raw data is done to get a smooth trajectory. This is needed for determining the velocity and acceleration, as we will use forward differencing on the position for this. On the graph below, you can see that the curve has become a lot smoother after regression.
Our robot model represents a real human arm. A human arm has 7 degrees of freedom. The first 3 are in the shoulder, 1 is in the elbow, and the last 3 are present in the wrist. So, our robot model also has 7 degrees of freedom. Each degree of freedom is represented by a cylinder. In order to perform calculations, we define some physical parameters of the robot. Those can be seen in the table on the left. We also calculated the inertia, as well as the center of mass of the links. Now we will look at two important kinematic functions: forward kinematics and inverse kinematics. Forward kinematics allows us to go from joint space to task space, meaning if we have the joint angles, we can calculate the XYZ coordinates. This is done by using the Dennevit-Hartenberg matrix. We can construct such a matrix for each link between the joints. When we then multiply these matrices, we get the XYZ coordinates of the end effector. Inverse kinematics does the opposite. It goes from task space to joint space. The calculations are quite difficult, so I won't discuss them here. Imposing the constraints of the joints of a real human arm, we get a solution for the joint angles. The joint velocities and accelerations, on the other hand, will then be calculated by forward differentiation.
After determining a feasible trajectory, we will now determine an optimal trajectory. For this, we want to punish torques, which is equivalent to punishing accelerations, but we want also to stay as close to the original movement as possible, as this is the task of a robotic arm. On the right side, you can see here an expression for the cost function. We see one term which punishes accelerations, and one term which punishes deviations in the position and velocity from the initial trajectory. Here you can see the result of our optimal trajectory, and we can see that the accelerations in the optimal trajectory have decreased significantly, with still respecting the movement of the robotic arm. We can call this optimization thus successful.
Computed torque control has been chosen to perform robot control. Therefore, a desired actuation torque is required to be applied to the joint motors. Starting from the equation of motion, actuation torques can be calculated based on desired joint positions, accelerations, and velocities. We can see that this equation contains an inertia term, a Coriolis and centrifugal term, and a gravity component. Going from joint motion to joint torques is called inverse dynamics, because calculating the inertia matrix and centrifugal and Coriolis component is mathematically impractical. The recursive Newton-Euler method is chosen to calculate the torque. Going from joint torques to joint motion is called forward dynamics. In forward dynamics, we use some interesting characteristics of the recursive Newton-Euler algorithm to calculate the inertia matrix, Coriolis and centrifugal term, and the gravity component. Since we now know all components in the equation of motions, this equation is now used to perform forward dynamics.
The functions that have just been defined will be used in the control scheme. The chosen control is computed torque control. This control will feed back the real measured movement and velocity of the robot and calculate the error with the desired one. This error signal is then multiplied with a constant and added to the input torque of the robot.
Simulating the real-life robot is done with forward dynamics. This indeed converts the applied actuation torques to the joint motion. Performing inverse and forward dynamics after each other would lead to a perfect reconstruction of the joint motion, and the control scheme would have no effect. In reality, modeling errors are present. In order to implement these errors in the robot simulator, some model parameters are changed within the forward dynamics function. Implementing computed torque control on our robot has led to the following control scheme. So, in this project, we have measured a desired trajectory. The measured data was then cleaned up and a regression was applied. Optimization was done to minimize acceleration, and this optimized trajectory has been simulated in a computed torque control scheme. When we perform all these steps, this leads to the trajectory in the figure on the right.